Hi. So I'm really happy to see you all here. I cannot see you that well, but I'm still really happy and excited. So my name is ELAJEV, and I'm from a company called ZeroTurnaround. And today we'll talk about monads, right? And we'll talk about Java 8 a little bit, and monads in Java 8. But the most important word on the slide and in this talk is well, it says unlocking, but it should be understanding, right? What we want to do here, we want to advance our knowledge. So before we start, because I really like to fit the presentation for the audience. So how many of you came here to learn something or to understand something better? Yeah, that's a good attendance, pretty much almost everyone. How many of you came here to just show your excellent knowledge of Haskell, algebraic types, and just to ask uncomfortable questions? I see 3 hands. That's good. That's good. So we'll mostly orient this discussion onto understanding things better. So first, let's talk about me a little bit. I'm a developer advocate at ZeroTurnaround, which is a product company. One of my main responsibilities there is to maintain and edit and publish blog posts and technical content on RebelLabs, which is our content portal. If you go check it out later, I'll be happy. You can find me and connect with me on Twitter. I know that there is an application for DevOps to ask questions and rate sessions. And you can ask questions there, but unfortunately, you cannot answer them there. And I couldn't get it working on my phone, so I would prefer questions on Twitter, if you mind. If you still ask there, we'll figure it out, but Twitter is the way to go. So ZeroTurnaround is a home where we do revolutionary tools for developers. We have 2 products, JRebel, XRebel. Simon Maple yesterday gave 2 sessions about each one of them. So if you would check them out, I would be happy, and my employer would be happy that I came here. So short intro is done. Let's go into the session. So what do we want here? What do we want to achieve with this, within this hour? We want to learn things. We want to understand what monad is, how to use that, how to recognize a monad when you see one, how to understand that a certain problem might be better solved by using monadic approach, learn some generic constructs and how to deal with them. And we want to solve a tiny real-world problem. I really like that. Well, I'm not very smart. I'm sufficiently smart to be here, but not incredibly smart. So I really like to think about small problems first and understand things based on those. So what we do not want to do here is to go really deep into technical details of algebraic types. We don't want to throw around words like ad hoc polymorphism and why is it better than parameterized polymorphism. So it will not be a very rigorous mathematical talk. There is a way into understanding monads, and many people did that way. But let's just take tiny baby steps into the concept, and for now we'll ignore some facts and simplify some things. So that's it. What I want to say here is obviously, we are mostly JVM developers based on JVM or mainly Java. Who works mainly in something not Java? Like Scala, Clojure, Groovy? Not so many. So mostly people are here Java developers. And for many years, people said that, OK, functional programming is not very good on Java, and it's not suited for that, and functions are not the first-class citizens. Well, you can see, even now with Java 8 and lambdas being here, and this big step towards functional programming on Java platform, still people are suspicious and not very convinced. Well, you can see that there are much more controversial things in the world than just functional programming on Java. A small Java 8 recap. So I believe everyone knows that, so we can introduce functional interfaces into our programs. So interface with a single method. We can reference those methods and assign them into fields to call them later, right? And we can use lambda syntax to organize our code in a block, right? I believe this should be, Java 8 has been out like for ages now. I believe this should be familiar with for everyone, right? Everyone seen those concepts. No one is confused. Great. So this is what we need for the code. So we'll have code examples, and that is the whole syntax that you need. Now let's get to monads. They are somewhat hard to grasp, and there is a controversial saying on the internet is that you don't understand monads until you understand monads. And then the first thing you do after you understand monads, you go and write a tutorial about them. That's why there are thousands of tutorials on the web, and you go there and you just lose yourself in them. And most of them take really, really mathematical approach to the concept, which is fine. And many areas in the world behave exactly like that, and that's the right approach. If you want to send a space shuttle to Mars, you better understand everything, and you start with physics, and you go from theory. If you just want to build a bridge over the tiny river in your backyard, you might start with quantum physics, and it might benefit you in life later, but you as well might just go and do that, right? So instead of going through the tutorials, we'll take a practical approach. So I'm a firm believer into problem-driven education. So we'll start with a problem. This little snippet of code is obviously JavaScript. I wanted to create a good example of Java code that illustrates the same problem, but it was getting too verbose. So what this code does here, it just attaches a function to be called on a certain event. So we want a button, an element button, fade somewhere, and when that's done, we want to log to the console something. So I believe everyone's seen just a little bit of JavaScript, so they recognize the concept and the piece of code here. This example of jQuery obviously can construct anything like that in any language. So in Java, this will become something like this, where the code is a bit larger, and then the main idea is that you provide callbacks to be executed at the end of a certain action, like when a certain event comes to life. And then you just pile and pile and pile those, and at the end you reach an event called a callback hell, right? So who knows what a callback hell is? There is a definition of a callback hell. So it's a term used by developers looking for a way to mask the fact they can't structure the code properly. It's obviously a joking definition, but it's very close to be true. So the idea is that if we just pile and pile code, at some point if it will come not easily maintainable, and we cannot do much with that. So what we want to do, we want to have a different syntax, and we want to have abstractions that will help us to organize code in a better way. So I would be really happy if at the end of this we could say just, okay, let's do this, and then when that's done, let's do this, and on the same level, without going deeper and deeper and deeper into the right, as we would do with callbacks, we just receive something out of every function call of that then, and we can provide the further interactions, right? So what we need to have here, we need to have a type, right? Java is a statically typed language, so everything begins with, well, often ends as well with types. And we need a type to, in this given problem, we need a type to represent an async result. There is such type in JDK, and obviously it was there for ages, which is Java util concurrent future, which can hold an object, and many methods can return that. What this future represents, it represents a result of a computation that will happen somewhere in the future. The interface of that is really simple. So you can ask if that thing is done, or you can just try to get the result. And the question now is, well, it has been present there for ages, so there was no problem with that. Now, the question is, can we do better than this? Can we do better? And indeed, we can. And now this part summarizes the problem. So we want to avoid callback hell, and given that it's a very limited problem that has been solved many, many times in the industry, I believe that we can manage to do that during this, say, 48 minutes that we have here. I know that I don't have any minute more than that because the lunch is next, so groups of people will start streaming as soon as we reach a moment that is more boring, or the moment the smell comes in. So we have this problem, and now we want to devise a solution to that. But another important aspect is that we want to use monads, right? We want to learn and understand what monads are, so we call them to the rescue. Don't be scared, don't go away yet. So this picture here on the screen depicts a piece of Haskell code. So this is a definition of a monad in Haskell. And don't be scared, you don't have to know Haskell. We will get there using plain Java. What I want you to understand here and to see here is actually this, a handwritten created picture that the definition of monad in Haskell is that just 3 lines long, right? Of course, there is a body of knowledge behind that, and there is syntactic sugar and everything, but it's just small. So we will get there. We'll get there in time for lunch. So we'll solve a callback hell problem with monads. And what a monad is, before we dive into the code, we need to understand what that is, right? And one definition is quite simple and very straightforward. A monad is just a monoid in the category of and the functors of X with product replaced and everything, and identity and the functor. This is not, I don't know the definition by heart. It's complex. It makes sense, it's very true. It's mathematically correct, but it doesn't help us to solve our callback hell problem here, right? And on top of that, we all know that, well, we all smart people here, so we get to the understanding. Everyone can do that, and we can as well. So we want to start with simple understanding. We want to start with a couple of metaphors, so to get the ball rolling, and then we'll iteratively improve on our understanding and get to the, not this definition, but, well, closer to that. So monad is, and it's often described as one of the items, like a box or a chain of elephants or a burrito. Or my favorite is actually the sequence of fish when the bigger fish eats the smaller fish and that eats something else. And it's very confusing because those things are very different, but they have 2 properties in common. So what they do and what they have in common, they have the ability to wrap things, right? Not with an elephant, but mostly boxes and burritos. You can wrap things and you can put things inside of the things or chain them together. And you can chain functions on top of that. So you can create, a container and then specify the functionality that you want to execute on the item inside that. So, and this is our intuition. We need to wrap things. We need to chain the functions, and we need this monad to be a type to be able to represent that in Java, right? So let's say that monad is a type, which is not exactly correct because monad is a type class. Who knows the definition of a type class? Just, there will be like half a minute, maybe 15 seconds, step away. So a type class is a construct that you can use to create classes. So for example, array list, which is not parameterized yet, is a type class, and if you parameterize that, you get an actual type. So a monad is a type class, but we will not go there tonight, because if we go there, that will lead us into differentiating, really having to understand difference between those, and that is the road to deep, dark places. we won't go there. So monad is a type for us today. So the wrapping functionalities that we want to achieve is pretty simple. So imagine we have this magical type, and we want this function called return or pure, which is two consistent definitions of how it's named in mathematical or other languages. So this function will take an instance of class A and return an instance of a monad that encapsulates that A, right? So if we think about terms of Java, this is quite clearly is a constructor method, right? This is like how you create your new types. It's a constructor method or factory method, and if we stop talking, being like really soft, and go and show pieces of code, that will look something like this, right? So we have an interface called monad. We parameterize that with value v, and we have a single method there that takes the value of type v and returns a monad. It's not a class yet because we want to specify the contract, as you remember that it wasn't just wrapping things, right? We need also the ability to chain and specify functions to operate on those things. And the contract for that in plain English would be something like this. So the name of this function will be bind, or the fish operator. I think it's a fish operator, but we'll call it bind. And it will take two things. It will take an existing monad over A, and it will take a function that can operate on this value A, and returns a different monad. And it will return the monad over B. So in terms of Java code, if English is not the best way for you to specify functionality, in terms of Java code, we'll have this second method in the monad interface, right? We have the method called bind. The existing monad of A that we had on the previous slides will be this instance, right? So we reside in the monad class, and so we have access to this because in the instance method. So we just need to provide a function that will operate on the values encapsulated by this, and will create a different a monad of a different type, right? So the definition of the bind will be this simple. Who's confused about this? Quite some people. So, but we'll get there. So we have an interface now. Let's say it does make sense. And let's try to maybe implement this interface and to create actual type that provides the meat of the code for satisfying this interface, and actually does something for us in terms of solving the callback help problem. So let's get into code. We will create a class called promise. It will represent a result of asynchronous computation, just like future. It will support our definition of a monad interface, and it will support binding functions into that and chaining the behavior with the bind. So imagine we have this class promise, and imagine it has the future-like operations is done and get. So we'll need to additional operations here. We'll need to be able to complete this promise with when the result is done, when the result is there. And for that, we'll use predefined methods with those names. So when the promise is done, somebody calls invoke, and whoever was waiting to get the value of that promise will get this value that is provided. And onRedeem would be our base definition of how we can provide callbacks, right? We just assumed that there is something because when we started with the problem, we had this idea that we already know how to write code that involves callbacks. So onRedeem method here, what we do, we give it a callback which will be executed when this promise is redeemed. So exactly as in the jQuery example that I showed before, when the button has faded in, we write into console the log statement. So when this promise will be invoked, then all the callbacks will be sequentially executed. So let's imagine we have that. Pretty simple. I don't want to show code here because we might run out of time, and we want to concentrate on actually specifying the monadic aspects of that. So let's go into implementing our interface that we had. So we start with pure, and if you remember that was the representation of a constructor method or a factor method. So we go with a factor method here. See how I'm already bending the rules of JVM here because we had an interface. So this should have been an instance method. But for the sake of simplicity, that's fine. It won't prevent us from getting things done and understand them better. So the definition of this pure method is incredibly simple. We create a new promise of the type this value, v. And since we have the value, we immediately invoke this promise with the value. So what it does in terms of monad, it returns an instance of a monad, which is a promise. It returns that, and inside that sits this value v. Right? So we encapsulated a single value in the context of the promise. So whoever is actually waiting for this, well, nobody can wait here because we don't leak it before, but whoever receives this promise and calls get on that will receive this value immediately, right? So we have now the pure functionality that takes a value of type v and returns a value of promise of v, right? Which satisfies the interface, if that would be an instance method. So with the bind, it's a little bit more complicated. First, we cannot make it a static method because we need an access to the original this instance. So what we do, the signature is quite simple. We have this function that we need to invoke on the result of the previous async computation. So imagine this there is no this in this code. Oh yeah, there is this. Look. So this represent a computation that will happen somewhat in the future. So what we do, we say, okay, here we can go with callbacks. We want to encapsulate this callback functionality into types, and we say, when the result of this computation noted by this is available, please invoke this callback. So what this callback does, it has access to another instance of promise called result. So it takes the result of the previous computation, it applies the function that we pass at the parameter, it applies that to the value that we get from the previous computation, and when the application result is ready, we take the final result value here and we put it into the promise that we can pass further. The code is a little bit convoluted because we deal with 3 promises here. So one is the this instance which we want to operate on. One is the second promise that is the result of this function that we pass. And one is the promise that we pass further. But in a nutshell, we do a very simple thing. We encapsulate the application of callbacks into a single method. So, and instead of providing the methods to run the callbacks further and further, we return the type that supports bind. So if I call bind on the result again and again and again, I will chain my functionality and they will be invoked one after other when the result of the first computation is done. So now we have both pure and bind, right? So we kind of satisfy the contract of a monad, but we'll do a get method as well. So it will come, first it comes very handy. I I literally love the code that you can drop somewhere and use and understand what's happening inside. So this would be our blocking debugging method, right? So what we do here, so imagine if somebody calls get on a promise, so we wait till the promise is done, and then we either throw an exception if something happened, or we return the result of that promise. So it's exactly like the future behaves, but I wanted to explicitly bring that up. So not only we can create this promise monad out of values, not only we can bind functionality, but we can kind of peek into the content of that. And this will come handy later. So now we have this promise code, and everyone is confused. I'm confused. So let's look at the example. Imagine we have a class that can return us promises. So we just call something, a method, that returns our promise that just wraps hello world. And on top of that, we just bind functions. So we can bind the function that takes a string and returns a promise of an integer. And this satisfies the whole contract that we had with being able to change functions. So bind takes a function from string to promise of integer. Pure takes just a value and returns a promise of that. And the resulting code will be working like that. So this should be a working example as long as we have something to provide our initial promise here, which we can easily do. So at this point, we have a checkpoint to understand how much confusion I created. So we have a class that represents a result of asynchronous computation. It knows how to handle exceptions and values, and it supports chaining functions together using bind. That is more or less clear, right? So who is confused by things that we have done yet? 3 people. We'll go through the questions and answers later. I hope we can find time for that, but bear with me. It will get easier as long as we get into the real code and not the hand-waving examples. So, but at this point, we have the promise, async computation, all good. We chain functions, we have pure, we have bind. So wait, is it? So did we just create a monad, and what was all the fuss about, right? If anyone, well, the code was straightforward. It wasn't maybe the most simplest and elegant solution, but anyone could write that, right? And a single interface, a single class, and just wrap code until it does satisfy the compiler. So, and the reason why we have this question is that we don't have a monad itself. A monad is, as we said before, the monad is a type class. So what we have here is an instance of a monad, right? So we have something that satisfies the monad construct, but it's not a monad itself. It's just exactly like parameterized array list of strings. It kind of is an array list of anything, but it specifies it more, right? Why do we have this distinction, and why is this distinction useful? Is because when we specify a more generic construction, like monads itself, instead of just working with instances of them, we can do fabulous things. We can do fabulous things with unifying the functionality that works on them, right? We have a common interface, and we can do generic functions that take monads in and produce different monads. And then in an ideal world, they will work with all of them. And we will just pass whatever instances of the monads we have, and they will work. So such common operations would be, for example, a sequence operation that takes a list of monads and produces a monad over list. That would be great. So we could just, for example, using the promises, we could say that I have the result of this asynchronous computation. I have a result of that asynchronous computation. And now I want an object that represents the result of both of them, chained in a list. Or we can zip different lists together. And this is all great, and this is all fancy. And some languages support that. It's kind of limited and awkward in Java, but it doesn't diminish its greatness. So a sequence, for example, would be represented like that. So you have a method somewhere, say static method or default method on some interface, that takes a list of monads and produces a monad of a list. Now, the hard part is that we cannot just take promises and stuff into this method, right? It wouldn't compile. What we can do is to hack our way around this limitation. So we'll just take the code of this sequence method and put that into the promise class and say that, OK, now we have the means to do the sequencing of promises, which I know is kind of unfortunate and maybe not as much as you would expect. But we can do things. We can get the code that works for everything, and there will be different pieces of code in different classes, but it will all follow the same functionality and the same rules. Again, we work on JVM, which is a platform that is different from others. So for example, to satisfy this contract, right, we will need to unwrap the values from those monads because for now, we just had pure and wrapping things and chaining functions, but we have no means of unwrapping things. So here would be like really tough to create a list of result values. So some languages, of course, have those implicit sugar, syntactic sugar things, and some languages have it easier and have an implicit get to unwrap things. This is a piece of Haskell code that you don't require to understand, but they use the value on the left side and on the right side, and they don't need to provide those get methods, which is rather fortunate. So in Java, we don't have that luxury. We operate in objects, so we'll need that get method. So we increase and enhance our interface with this unorthodox and not very monadic get method, right? So the good thing is we just implemented that several slides ago. So we were very lucky in that regard. It's easy to be lucky during the session, but we get it. So now we have the pure functionality binding to satisfy the contract of a algebraic monad, and we have get to make actually this code usable. So now we definitely have the monad, right? Who thinks that now we have a monad that we can work with, then we can pass values, that we can chain them, we can sequence, have higher order functions, and all this greatness? 3 people. Good. So the deal is it's not so simple and not so fast. So not only the biggest impact what monadic code gives you is that every one of those instances of monads, they play by the rules, right? You can write code in in very different fashion and manners. Your bind method can blow up the universe, and if anyone will use your monads and your code using higher order functions on anything, and they would just expect everything to work as it should, and you blow up the universe, they will be sad, right? So there are laws that govern monad behavior, and all well-behaved monads should abide those. So there are 3 of them. So a monad may not injure a human being, or through an action allow human being come to harm. It should obey the orders given by human beings, and it must protect its own existence unless it's nope. It's not those laws. It's different. It's robotics. So the laws of monads are right here. So again, Haskell code. We will translate that into Java code immediately. There are 3 of them. Three laws. So the first one is very simple. It's the left identity rule. What you want to have is you want to specify that bind doesn't behave unexpectedly. So the bind contract was that we have a monad, we have a function to operate on the value inside the monad, and we return a different monad. So what a good behaving monad should do, it should satisfy this equality with a fancy triple equal operator, which we'll define a little bit later. If we take a value and wrap it into our monad, and then we bind the function there, the result, in a nutshell, should not be very distinguishable from applying this function on the value itself. So if we would break this rule, it will kind of make our bind unusable. The right identity is the second rule, and since we have just two functions, this verifies that pure behaves well. Right? So if we have a monad and we pass the identity function that does, we bind the pure function that just takes the value and creates a different monad, we would expect that the result would not be different from what we started for, because, well, it's just reasonable. So we have the rule that says the bind is correct, the pure is correct, and then we have a third and obviously most complex rule that if you bind two different functions together, like if you chain the bind invocations, then the result is kind of the same as if you just apply those functions one on top of each other. So if you just apply the first function and bind the second. So this is required to avoid blowing up the universe when you actually want to use your code as in an actual software, not on slides, right? So some languages will have it easy. So now the question is about those tiny fancy equality operators. So obviously we cannot just get like double equals operator, because that doesn't work even for simple objects on the heap, right? We cannot use equals because, well, that would be rather unfortunate, because our promise operations were returning new objects all the way. It would be just like sad if even our simple example wouldn't satisfy that. So let's define this equality thing more or less rigorously so we can reason about it. So it's not to make your software formally correct, but to allow you to reason about this. Some languages have it easy. If you have referential transparency and all the function invocations are the same as all the rest function invocations, like you call system out twice with the same arguments, and those can be substituted for one and each other, that's all good. But for moral platforms like JVM, this is different. So there are those pesky hash code and equals. There are inequality of objects. So what we want in Java, we won't just say, OK, we give up. We want just an ability to reason about this code. So we say the side effects of those applications are similar, right? If the left side doesn't blow up universe, let the right side not blow up universe as well. There will be corner cases when you have to dig deeper, but in a nutshell, that's more or less enough for purposes of playing with code. So we want the get operators observes the same values, and we want, if one side blows with exception, we want the other side to blow with exception as well. So now if we define this like that, then we can say, OK, the promise code satisfied the left identity rule, which is depicted right here. So if we have some predefined set of data, then if we just wrap a value into the pure and bind the function f and observe the result would be the same if we just apply the function to the value and observe the result, which is a direct translation of the kind of fluffy English definitions that we gave before. The good thing is, and I can do the right identity as well, the good thing here is that you can verify that your monads and your instances of monad kind of abide the rules that they should. And you do that very simply, as we do in software projects. We write tests for them, right? Who writes tests? Yeah, exactly. See, you have all the tools to create your own monads. So a checkpoint here will be create a class that kind of satisfies the interface. You might or might not want to actually even bring the interface into your class path. Just you can operate in the pure classes, since we are limited in the higher order function use. We write tests that pure and bind behaved well, and we just start using that. And as you can see, so this example of the code, our binding functions together will not take us right to the callbacks forward, forward, and forward. What it will keep our code straight, and we will and we will provide the functionality at the same level all the time, which is much simpler because we have those convenient types that we spent 40 minutes defining. That's productive, I would guess. So obviously, here should be a disclaimer. I have the code for that available on GitHub, so if you want to just a tiny class that satisfies the monad laws, you can just look at that and use that. But like, don't put that into production. Well, because that is first code written by me. That should be enough reason not to put that into production, but without sufficient testing. But the second reason is that in JDK 8, there is a class that represents a result of asynchronous computation that allows you to change the behavior and provide the functions to operate on the previous values. And the class is obviously Java util concurrent completable future. That would be really sad if I just said that it's there and let's spoil the whole journey to that. But it is, and it's really useful. And the interface of that and the API of that contains a number of then apply, then accept, then apply async methods that take functions and make those functions execute when the result is present, which is exactly our definition of a bind. So this is, well, there is no proper code here, but it looks very similar to the bind, right? We have the instance of a completable future, and we apply a function later. And if you say apply async, then by magic, it will just use the common function pool to provide this parallelization for you and to execute your binding function bound into this completable future in the background. So completable future is an instance of a monad in a nutshell. You can look into that. You can see that actually it is in JDK. You have means and opportunity to create monadic code and put that into JDK. There are other examples of monads in the code, official JDK code. So one of them is illustrated by this awesome picture of Schrodinger's cat, so which is either dead or alive based on the observation of the experiment. So, and the monad that I try to illustrate with this is obviously an optional. So an optional is the type that represents a value or absence of one, right? So either we have something in there or not, and we have the means to specify, to create an optional out of pure values. And this is obviously the definition of our pure method. And we can do the same with a null and return an empty optional. And we have a bind that is a flat map, which is a common name for monadic operations. So it's really maybe rather unfortunate that completable future used then do something and doesn't use map or flat map. So the flat map follows our bind definitions exactly. So it relies on the instance of this being present. It takes a function from the value of the original optional into a different optional, so from the value to the monad, and it returns this new monad. And if you can see, the code is kind of really similar to what we had in present. So if the value is not present, return empty. If the value is present, get value, apply the mapper, and file the new optional. There is also a map function that takes the regular function that doesn't return an optional. It kind of still provides an optional functionality. So they're different. So flat map is our bind. Off on an optional is our pure. Completable future works. And this kind of summarizes this whole session. So what we did here, we talked about we talked about means of understanding. We started with a simple problem, which might or might not be very relevant, but it's like very encapsulated. We derived a type to understand this problem better. We derived that to be able to write code in a monadic fashion, and we create our small framework of being able to write tests to show that our monads work as expected. So why do we do that? One of the main takeaways of the session that I want you to have is that knowing your tools and knowing things that you can or cannot do with what you work on constantly is really important. And it's really easy to embarrass yourself in front of your team or colleagues or internet if you are not paying attention. So the best way to learn is to go and do something and try to play with the code. Just go look into completable future code, go look into how optionals work. Maybe they will be a right tool to solving your problems. You will at least recognize patterns when monadic code works or when it doesn't work that well. So with this, that's all. This is all I have. I'm conveniently have 30 minutes till the end of the session, so it's 30 minutes till lunch. And we have time for some questions. So yeah, if you can go into URL, you can download the trial, you will get a t-shirt. Products are awesome, and you should look into that. You can contact me, you can find the code for our promise code on the GitHub, tweet at me, email me, and it's questions time. Any questions? Okay, I cannot see any hands. Maybe it's just me seeing not very well. But I think that's all. If anyone has questions, we can talk privately.
I have a question. Will the operations on monad, the pure bind and get, reminds the operations on Java 8 stream? Is Java 8 stream a monad?
So the question is, that's a great question. So the question is, the operations of a monad that we defined is pure bind and get remind very much as operations of Java 8 streams. So the natural question is a stream a monad? Oh, that's cool. Like, you're listening. That's amazing. So it's a really good question. It's a twofold question, so there are two answers. So if you want to go into any programming language community with the statement that Java 8 streams are monads, that is not the most wise thing to do. They are essentially not monads, right? There are actually, well, monad is an algebraic type that is governed by rules, and there are certain properties that you have to implement. So they're really hard to distinguish, at least like for the equality, or we didn't have the proper equality on JVM. So I wouldn't go that far to say that streams are proper monads, but what I would say that streams, Java 8 streams, provide you the means to write monadic code, right? So they expose those operations. For all practical intents and purposes, they allow you to write monadic code. So I would say if you use that inside of your project, I would think about them as a monads. If I would have to go and talk to people that might ask uncomfortable questions, I would be more humble about that. But I'd go with a monad. I like them. Any more questions? We still have 10 minutes. You will still be first in the queue for lunch. Okay. See you online. Oh, see you like in an hour. I have another session here, so